So this morning, well, at least it's morning now while I'm making this, we're going to finish up with the last example for this law of sines. And as I've written here on the top of the notes, this is what we refer to as an ambiguous case, where the information we're given is two sides, two lengths of the sides of the triangle, and only one angle. So because we only know one angle, that gives us a sense of mystery, if you will, as to what the other possible angles are if there's a possibility to get three angles. In this example, when we take a look at it, we're going to solve, which means we're going to find all the angles and all the sides, the lengths of the sides of this triangle ABC, where we have one angle, A, 35 degrees, and we have its partner size. So we have enough information here to make a ratio. And then the other side that we're given is B. So let's start with what we're given. Our ratio can be A over the sine of A. And filling in the information from our example, this is going to be 12 over the sine of 35 degrees. So we're able to establish that ratio. The other information that we're given is the length of side B. So we're going to have this 16 up here in the numerator, and then down here we are going to have the sine of B. Because we don't know what that is, that's what we're going to solve for. So as we've been doing, we're going to do a cross multiplication, which will give us 12 times the sine of B is equal to 16 times the sine of 35 degrees, and then dividing both sides by the 12, we end up with the sine of B is equal to 16 times the sine of 35 degrees, all over 12. And as I said in the other examples, there's two approaches you can take here. One is to do inverse sine of this information here, which will give you your B directly. The other approach is to do this calculation in this fraction here, which I'm going to do just to show you that in case that's the method you like. And this gives us, when we do this calculation, this gives us approximately 7648. I rounded to 4 decimal places. So the sine of this unknown angle B is 0.7648. When we do inverse sine of this ratio here, we get that B is approximately equal to the angle 50 degrees. And as I said in the other video, and I'll repeat because this is an important concept, we know that sine is, or I am desperately hoping you know this at this point, that sine is positive in both Q1 and Q2. So this angle here, 50 degrees, this is our angle from Q1, but we also have to consider the angle from Q2 that would also work, because remember, between Q1 and Q2, we have angles between 0 and 180, and those are all possibilities for our triangle that has angles that add between 0 and 180. So to find the reference angle in Q2, we would do pi, or 180 degrees, minus 50 degrees, and this gives us 130 degrees. So another possibility for B is going to be 130 degrees. Now, how do we know if we can use this or not? The check that we're going to do is we're going to take this 130 degrees possibility, which is our angle B here, and we're going to add it with the angle we already have, which is angle A, 35 degrees. So 130 degrees and 135 degrees. This is 165 degrees, which is less than our 180, less than our 180 degrees. So this says, yeah, we can use this 130, because if we add the angle we know, A, and this possible angle B of 130, we're at 165, so we're still left less than that 180 to get a third angle. So this example, we're going to have two potential triangles because we have two possible values for our angle B. So what I'm going to do here is I'm going to say, so two triangles. So we have two different triangles we're going to be constructing. And let's call one, not very creative here, but let's call one triangle 1. And then let's call, you know what, I'm going to switch up a color to make it obvious. We have two different ones. And let's call the other one triangle 2. So we have triangle 1 and triangle 2. So for triangle 1, I'm going to take a look at the angles first, since that's what we've been focusing on. So for triangle 1, we know A plus B plus C is equal to 180 degrees. And we know that angle A is 35 degrees. For this first triangle, what I'm going to do is I'm going to use the angle of 50 for B. So we have 50 degrees for B, plus C is 180 degrees. And solving for C in this triangle, we get C is 95 degrees. So in this triangle 1, our angles are 35, 50, and 95 degrees. So I'm going to come over here now and do the same thing for triangle 2. Again, we know that all three of these angles have to be equal to 180. No changes with our angle A. That's the 35 degrees we were given initially. But now for B, I'm going to use this angle from Q2 of 130 degrees. So now when we solve for C, we have angle C is 15 degrees. So we're able to construct, because the information we originally given was not specific enough, we have two possible triangles. Which one is it that truly exists? We don't know, and we won't figure that out. That will remain an unsolved mystery, but we know that there are two possibilities. At this point, we have all three angles. We have angle A, angle B, and angle C for both triangles. And going back to our original information here, we have the length of A and the length of B. So the missing information now at this point is just the length of side C. And to solve for that side C, we are going to use our law of sines that we've been using. And coming back here, we're going to use this same ratio that we have for A to solve for side C. So we're going to have our 35 degrees and our 12. So the ratio we're going to use is 12 over the sine of 35 degrees, same ratio that we didn't use that ratio yet. 12 over the sine of 35 degrees. Well, yeah, sorry. I can't even read on top of the screen here. We did use that same ratio there. So we have 12 over the sine of 35 degrees, but this time we're going to use it to solve for the length of a side, C, and this is going to be over, in this triangle, the sine of the sine of 95 degrees, because we're using this value for C. So again, with our cross multiplication, we have 12 times the sine of 95 degrees is equal to C sine of 35 degrees. So C is going to be equal to 12 sine 95 degrees divided by the sine of 35 degrees. Hopefully at this time you're seeing how we're going about solving these. In this case, divide both sides of the equation by sine of 35 degrees. And when we solve for this, we're solving for the length of a side, so no reason to use inverse sine function. We're not looking for any angles, we're looking for the length of the side. And so when we solve this, we get C is about 20.8. We were asked to round to the nearest tenth, So, whoops, there is the length of our side C. So now let's come over to our triangle 2. So triangle 1 is complete. We have all 3 angles and all 3 sides. And coming over to triangle 2, again, we have all 3 angles. We have 2 sides. And again, we need this side C. So I'm going to use the same ratio here on the left. And we have 12 over the sine of 35 degrees. And this is equal to C. But now we're going to be looking at the sine of 15 degrees because for this triangle, the second triangle, our C is now 15. Cross multiplying, we have 12 times the sine of 15 degrees is equal to C sine of 35 degrees. Divide both sides by sine of 35 degrees, and we get C is equal to 12 sine 15 degrees over sine 35 degrees. And then finishing up this calculation, C is about equal to 5.4. So 2 different triangles. And you can see the relationship here that in this first triangle, C, 95 degrees, had a length of 20 degrees. Here, C, 15 degrees, it's a much smaller length, so the length of its opposite side is also going to be a much smaller or shorter length. So that's something to keep in mind when you do these problems, that the length of a side corresponds to the angle it's opposite. So when you get your answers, you should be able to see that kind of relationship.